So today I'm just going to talk to you about liquid structure under extreme conditions and my research using synchrotron X-ray diffraction and neutron diffraction combined with levitation with laser heating and high pressure methods. Okay, so before I really begin this talk, I just want to acknowledge some of my co-authors, particularly those in Bristol in the School of Earth Sciences, Oliver Lord, Mike Walter, who's now in Carnegie Institute in Washington, Simon Cohn and Benedict Heinen, and here in physics, Francesco Torchi and Adrian Barnes, and of course others, particularly those at central facilities who contributed to this work. So liquids, as we know, the liquid state is an intriguing phase, intermediate between that of a gas and ordered solid, and where the atoms in a liquid move around chaotically, like in a gas, but they're also bound by strong intermolecular forces to form a relatively incompressible condensed state with solid-like densities. And so liquids occupy a relatively narrow pressure temperature regime, and as a result, they're one of the least prevalent states within the known universe, and where their very existence is contingent upon a delicate balance between these cohesive forces which impede vaporization and entropic forces to prevent crystallization. Yet despite their precarious nature, the liquids play a key role in sustaining life, life on Earth, both as the active matrix for cell or molecular biology, or for driving geochemical processes which are essential for maintaining our habitable planet. So I'm particularly interested in how liquids and their structure change at extreme conditions, and by this I mean high temperatures and high pressures. And this is important because changes in liquid and melt structure in the interiors of planetary interiors can control the physical properties and behavior of magma at depth, which in turn controls geochemical and geophysical processes. Also, there's the possible existence of abrupt and reversible liquid-liquid transitions at high pressure and high temperature conditions, and which is important for the discovery of new exotic liquid phases, and is important for the development of new materials with potentially unique physical properties. And so an example of this, for example, is liquid phosphorus, which is perhaps one of the few convincing materials which has been shown to undergo a liquid-liquid transition. So here's the structure factor measured for liquid phosphorus, and there's a distinct change in structure over a very abrupt pressure range at elevated pressure, where the liquid structure changes from a molecular liquid insulator to a metallic network structure. Okay, so where do we find liquids at extreme conditions? So under ambient pressure conditions, it's important to understand liquid and melt structure for industrial melt processing, in order to develop new materials, for example, such as novel glass compositions, and also for modeling material response to extreme conditions. So for example, liquid metals are used as heat transfer media in nuclear reactors and concentrated solar energy plants. And of course, understanding melt structure and changes is important in liquid rocks in order to understand volcanic processes. At high pressures, changes in melt structure affects the behavior of magma at depth, with implications, for example, in planetary formation, or the differentiation from a primordial magma ocean. And metallic melts in particular are important for core formation processes and understanding planetary magnetic field generation. At very extreme conditions, it may be possible to form exotic states. For example, liquid metallic hydrogen is predicted in the deep interior of the Jupiter gas giant planet. So it's not possible to access directly the extreme conditions, obviously, in the deep Earth and deep planetary interiors. And so to probe a liquid structure, it's necessary to reproduce these extreme conditions in the laboratory. So at 1 atmosphere pressure conditions, we can generate high temperatures using conventional furnace methods or wire heaters. Or for very high temperatures where it's impossible to contain a sample for oxide melts or metallic melts, for example, we can use the method of levitation with laser heating. To generate high pressure conditions, we rely on the relatively simple principle that pressure is equal to force over area. So it's possible by maximizing the force applied onto a sample to generate moderately high pressures, lithospheric conditions, for example, or pressures corresponding to the lunar core at pressures up to around 5 gigapascals using this piston cylinder technique. And at higher pressure conditions, for example, those corresponding to Earth's upper mantle, we can use larger scale multi-anvil press shown here, where we can access upper mantle conditions 25 to 30 gigapascals and 2000 Kelvin, for example. But the conditions within the very deep Earth at the core mantle boundary, for example, are in excess of 100 gigapascals and 3,000 or 4,000 Kelvin, and the pressure in the center of Earth's core is 360 gigapascals. So in order to generate these very extreme conditions, we have to use a different approach, and we tend to use the diamond anvil cell. And here we generate extreme pressures by minimizing the cross-sectional area of our sample that the force is applied over. And so using the diamond anvil cell technique, compressing a microscale sample between the tips of two diamonds, we can routinely generate conditions within planetary within the lower mantle of the Earth and planetary cores. Okay, so once we've generated these extreme conditions, we have our melt at high temperature or high pressure. It's necessary to measure the melt structure. And for this, we need to know the bulk structure. So we need a deeply highly penetrating probe. So we use high energy X-rays from synchrotron X-ray diffraction or neutron diffraction techniques. And so this is a photograph of the European Synchrotron Radiation Facility and the Institute Langevin reactor neutron source, both in Grenoble in France. And these facilities generate either high energy synchrotron X-ray beams or beams of neutrons, which are then supplied to a wide array of different beam lines for users to perform their experiments. And the general principle of a neutron or an X-ray diffraction experiment is shown here. So here we have an instant beam of either synchrotron X-rays or neutron with an instant where the magnitude of the instant wave vector is 2 pi upon lambda, where lambda is the wavelength of our instant X-ray or neutron. And typically the wavelength of an X-ray or a neutron is comparable to the distance, the atomic spacings in a material. So the instant X-ray or neutron scatters from our sample, and we can measure a diffraction pattern, a two-dimensional diffraction pattern, as a function of our scattering vector, with elastic scattering vector, which is defined as 4 pi divided by the wavelength multiplied by sine of 1/2 of the scattering angle. And for liquids and glass materials with a disordered structure, we observe these diffuse broad scattering rings compared to a crystalline solid, where you would observe very sharp, well-defined Bragg diffraction rings. So integrating the two-dimensional diffraction pattern, we can obtain our so-called total structure factor, shown here for SiO2 glass using X-rays or neutron diffraction. And the total structure factor is the weighted sum of all the individual pair correlations in the system. So for if you have a sample with n chemical elements, you have n times m plus 1/2 atomic pairs. So in this case, these are the structure factors for silica, SiO2. So we have 2 chemical elements, and so we have 3 atomic pairs, which sum together to make up our total structure factor. And the weighting factor on these individual pair correlations are different depending on whether we use X-rays or neutrons. So the X-ray form factor, for example, increases as a function of atomic number. So we probe heavier elements much more strongly than neutrons, where it's possible to probe light elements, including hydrogen and oxygen. And so the two techniques are very complementary. We can Fourier transform our total structure factor to obtain our real space information in terms of the pair distribution function, which gives us essentially a probability distribution of finding an atom at a distance r from another atom centered at the origin. So a little bit more information about the pair distribution function is shown here. So as for the total structure factor, the total pair distribution function is the weighted sum of all the individual pair correlations in the system. So shown here is the pair distribution function, G of R in black, for this simulated SiO2 structure. And we can see that the first peak arises from our nearest neighbor silicon oxygen bond distance, with a second peak arising from the oxygen-oxygen distance in a SiO4 tetrahedron. At higher distances, we have overlapping silicon-silicon and other higher order correlations. And so experimentally, it's difficult to resolve these individual correlations beyond the first coordination shell. So the aim of our experiments is to obtain as much detailed information as possible on these individual pair distribution functions in order to obtain the maximal structural information that we can on the liquid, and which we can then compare to our simulation methods. So the first case I'm going to discuss is regarding the atomic scale structural constraints on glass formation in the calcium aluminate system. So if we consider the conventional definition of a glass is an amorphous solid, shown here, which is formed from a liquid via rapid quench. And in this way, the atoms do not have sufficient time to organize themselves into an ordered crystalline solid. And so the glass forming liquid undergoes a continuous transition through its glass transition temperature into an amorphous glassy state. We consider liquid alumina, Al2O3, shown here on the left of this phase diagram. It doesn't on its own form a glass. It just has the wrong stoichiometry. It's unable to form a glass material. However, we can add other cations, other oxides to alumina to form glass, and so in the calcium aluminate system, this hatched region around the eutectic represents a traditional glass forming region in the calcium aluminate system. We can extend this glass forming region by using containerless techniques. So, for example, using aerodynamic levitation with laser heating. This allows for more rapid quenching, so we can access deeper supercooled states, and it also prevents contamination and avoids heterogeneous nucleation from the sides of any container. And so using this technique, we can significantly enhance our glass forming region. And I'm going to concentrate talking about the equimolar composition here, which I'll refer to as Ca, and the calcium-rich end member of this enhanced glass forming region, tricalcium aluminate, or C3A. So the experimental setup for a synchrotron X-ray diffraction of a levitated sample is shown here. This is our setup at the ID11 beamline at the ESRF. And our sample is levitated against gravity on an inert gas, in this case, typically argon, and melted using two lasers. We have two 100-watt CO2 lasers incident on our sample from both above and below the levitation nozzle. And we can probe the temperature of the sample using a pyrometer and monitor the sample in the safety away from the experimental hut using a video feed. And then we have high energy X-rays instant on our liquid sample and scattered to be recorded on our CCD detector. And this setup is optimized for both long static measurements and fast millisecond acquisition, so that we can monitor structural changes during from glass forming liquids during solidification. So very briefly, I'll just go over the data reduction for a synchrotron X-ray diffraction experiment with for a levitated liquid sample. You can see here in blue we have the total scattering, and then our background scattering in red, which is really quite small. This since it's a containerless technique, most of the scattering is coming from the liquid sample, and our background mostly comes from air scattering. So we subtract this background, normalize it to the self and incoherent scattering, the Compton scattering, so that then, which we then subtract in order to obtain our total structure factor, which contains the coherent structural information of the liquid. So here I show a series of structure factor measurements for the Ca, calcium, equimolar calcium aluminate liquid, and tricalcium aluminate liquid, as the liquid is supercooled from high temperature through its glass transition into the solid glassy state. The first thing we can observe is a clear evolution in this first peak, so-called first sharp diffraction peak, from cooling from the high temperature liquid into the glass. And if we look at this more closely, the top panel here shows change in height of this peak, change in its width, and changes in position over the supercooled region. And this peak is highly indicative of changes occurring in the melt structure on a medium range length scale. And we can actually, at least for the equimolar composition, see an inflection in this change in the supercooled region. And this coincides with, this occurs at around 1.25 times the glass transition, which coincides with the so-called dynamical crossover temperature, below which dynamical arrest tends to begin in glass forming liquids. So these synchrotron, fast synchrotron measurements during solidification indicate some substantial changes occurring in medium range order. It's advantageous to use some element selective techniques to probe the aluminium and calcium coordination environments in more detail to really see what's going on during the glass formation. So here we turn to neutron diffraction, and this is an example of our setup at the D4C neutron diffractometer at the Institut Langevin. And we have a similar setup to X-rays. Neutrons come into the sample, which is levitated here inside the instrument bell jar, and it's heated from these two lasers from above. Except instead of a two-dimensional detector array, we detect the scattered neutrons using this this array of detectors at fixed scattering angle. And in fact, this entire detector bank is on these air cushions and moves during the experiment to make sure there's no gaps in measured scattering angle. So here I show a example of the scattering intensity during a levitation experiment at D4C, and we can see that as for X-ray diffraction, our intensity is more or less what you see is what you get for a liquid structure factor measurement, although the levitation gas gives rise to slightly higher background due to the higher scattering length of argon for neutrons. So, but with neutrons, we can take advantage of the fact that the scattering length varies not only between elements, but also isotopes of the same element. So, for example, we see a large scattering length contrast between hydrogen and deuterium. The 36Ar argon isotope scatters much more strongly than other natural isotopes, and we see this trend all along the with increasing atomic number. There's no real trend. And we can use this to gain insight, for example, on the calcium environment by applying the method of neutron diffraction with isotope substitution. And so this was actually a technique, as Bob mentioned, developed by Bristol's John Enderby, where we take we can take different isotopes of the same element. So in this case, 44 calcium 44 and calcium in its natural isotopic abundance have quite a large scattering length contrast. And so if we can take free samples, synthesize free samples that are identical in every respect, except for they contain either calcium 44, calcium in its natural isotopic abundance, or 50-50 mixture of the two, then the correlations involving calcium will have different weighting factors. And so this leads to observably different structure factors. And so here I show the neutron diffraction with isotope substitution measurements for the equimolar calcium aluminate liquid and its glass, and the tricalcium aluminate liquid. And we can see that between the natural mixture and 44 structure factors, there's a contrast, at least in this low Q region, due to the different weighting factors on the correlations involving calcium. And so we can subtract and make linear combinations of these structure factors in order to isolate or eliminate specific pair correlations of interest. So I illustrate this here with the real space pair difference functions. And so in this first order difference function, the structure factors were subtracted and Fourier transformed. So we've eliminated all those correlations that involve calcium, and we see a very well-defined aluminium oxygen peak here, which we can integrate over this peak and obtain very reliable values for our average aluminium oxygen coordination number. So for calcium and aluminate liquid, we find aluminium oxygen coordination number of 4.2, which changes dramatically on glass formation to around 4 in the glass. And similarly for C3A liquid, we find coordination number of 4.1. Similarly, we can combine the measured structure factors to eliminate all those correlations which don't involve calcium. And so here the aluminium oxygen peak disappears, and our first peak arises from our calcium oxygen nearest neighbor bond length. And again, we can integrate over this peak and obtain very reliable values for the average calcium oxygen coordination numbers, which are around 6. We could take this one step further still, and because we have free structure factor measurements, we can combine all three in such a way that we can eliminate all other correlations aside from calcium. And so here we can directly obtain the calcium structure, partial structure factor, and here the calcium pair distribution function. And in fact, this represents the first measurement for C3A liquid of the first application of neutron diffraction with isotope substitution to obtain a partial pair distribution function for an oxide melt. The red curves here, the dashed red curves here, are from molecular dynamics simulations, and we can see actually they're in very good agreement with the simulations are in very good agreement with the experimentally measured difference functions, and even on the partial structure factor level. And so this gives us very good confidence in our structural model obtained from simulation. So to summarize the structural constraints on glass formation in this calcium aluminate system, first for the equimolar Ca composition, we observe a significant fraction, around 20% of the aluminium are in highly coordinated ALO5 units, which is with a significant fraction of oxygen triclusters, which are incompatible with glass formation. So this explains why, under ordinary circumstances, the equimolar composition doesn't form a glass. However, using levitation and deeply undercooling the melt, these structures break down, and we're able to form an almost entirely corner-shared tetrahedral glass network. And this is accompanied by an increase in medium range order, which is associated with the development of chains of edge and face shed calcium sensor polyhedra shown here. And this is what contributes to the development in medium range ordering, which we observed in our fast synchrotron X-ray diffraction measurements of solidification processes. For the calcium-rich end member of the glass-forming region, tricalcium aluminate C3A, despite this being a depolarized composition, the liquid is largely composed of an infinite network of ALO4 units. However, we observe around 10% of unconnected ALO4 monomers and Al2O7 dimers indicated by these red and yellow units in this simulation model. And we observe that the number of these isolated units increases with increased calcium content. And so this can explain the limit of glass formation, since the tricalcium aluminate composition represents a threshold beyond which the glass can no longer support an infinitely connected network. Okay, so moving on from ambient pressure liquid diffraction measurements, I'm going to talk about some high pressure liquid diffraction measurements. As mentioned earlier, there's several ways to generate high pressure conditions to measure, and early structural measurements of liquid at high pressure used large volume multi-anvil techniques with energy dispersive X-ray diffraction to mitigate against the fact that we have very limited scattering angle accessibility due to these huge multi-anvils which get in the way of the scattered beam. Another large volume technique using a Paris-Edinburgh press was developed to optimize the scattering angle accessibility, and actually this has been successfully applied with resistive heaters to measure liquid structures at high pressure with synchrotron X-ray diffraction. However, for very high pressures, we need to use the diamond anvil cell. And actually, diamond anvil cell has advantages in that the diamonds are relatively transparent to X-rays and optical wavelengths, so we can monitor the behavior of materials in situ using X-ray diffraction or optical spectroscopy techniques. And we can heat our sample in a diamond anvil cell by equipping it with resistive heaters, or using laser heating, where we pass infrared laser beams through the transparent body of the diamond to heat our sample under compression. So I'm going to consider some high pressure liquid metal structure where at ambient pressures liquid metals can be approximated more or less as simple liquids. And by this I mean their atoms arrange in an optimal packing similar to ideal hard sphere structures. And so I show here in this example for liquid iron, measured in a laser heated iron anvil cell to pressures up to around 60 gigapascals by Shen et al. And they observed very little change in the structure of liquid iron with increasing pressure. And in fact, at 60 GPa, liquid iron remains consistent with a close packed hard sphere liquid. But this isn't not always the case. We see liquids can have a complex structure. Let's take water, for example, and at ambient conditions, water has this complex structure. But with increasing pressure, increasing densification, water undergoes a transformation and actually behaves more like an ideal liquid, simple liquid at high pressures. But again, this isn't a given that liquids will transform to simple behavior at high pressures. For example, liquid rubidium behaves like a simple liquid, has a simple liquid structure at low pressures, but undergoes a simple to complex liquid transformation at high pressures. And this is indicated actually by the splitting of this first peak in the structure factor. We see the development of a shoulder and a new peak, which we also see in our water structure factor for water, which disappears when it becomes a more simple liquid. We can understand some of this behavior as it coincides with unusual. This behavior coincides with unusual behavior in the melting curve. So, for example, this is the phase diagram for water, and we see a negative slope in the melting curve with increasing pressure until it becomes positive again, and this coincides with the low density and transformation to high density phases of water. And this negative slope on the melting curve can explain some of the remarkable properties, for example, of water. For example, the volume expansion from liquid water to ice at ambient pressure. And if we consider the Clausius-Clapeyron relation, the melting curve can be understood by the change in volume divided by the change in entropy. So for a liquid, the entropy is always greater than that of the solid from which it melts. And the volume change on melting is also usually positive. But if we have a negative melting curve, this implies an increase in density on melting. So similarly for rubidium, we see the simple to complex structure transformation coincides with a maximum in the rubidium melting curve. And in fact, rubidium undergoes several maxima and minima in its melting curve behavior, coinciding with transformation, polymorphic transformations taking place in crystalline solid state. So I'm going to focus on some measurements which we made at high pressure on liquid gallium. So gallium's a remarkable metal. At room temperature, it crystallizes into a complex orthorhombic structure with mixed metallic and covalent bonding. And this gives rise to some unusual characteristics, including its anomalously low melting point. So metallic gallium will melt in your hand or in your tea. And the implications of this means it has one of the largest liquid stability ranges of all the elements, and similar to water, undergoes a 3% volume expansion on solidification. And so it also has this negative melting curve initially. And actually this is interesting because at room temperature, all you have to do to melt gallium in a pressure cell is to squeeze it. And so with increasing pressure, the melting curve goes down until around 1.2 gigapascals when it starts to increase again. And the structure of the high pressure gallium liquid previously wasn't much was known, and so that's why we decided to look at it. And so we used a membrane-driven diamond anvil cell equipped with an external heater. So the whole diamond anvil cell heats up, and our gallium sample is placed within a sodium chloride ring in order to isolate it from the rhenium metal gasket. And then the whole diamond anvil cell assembly is placed within a vacuum vessel at beamline I-15 at the diamond light source, and we have a highly focused X-ray beam instant through our liquid sample pressure, and we measure the liquid diffraction pattern as a function of pressure. And I combined these measurements with some ab initio molecular dynamics simulations. And so these use the VASP code, which I ran on Bristol's ACRC Blue Crystal 4 supercomputer. So ab initio molecular dynamics computes forces computes the electronic forces on atoms by solving the many-body time-independent Schrodinger equation. And at each time step, the atomic configuration is evolved using classical Newtonian mechanics. In this case, I used 600 atoms in each simulation cell in order to accurately reproduce the measured structure factor. And I used the MVT ensemble, so the number of atoms, volume, and temperature remain the same during the simulation, where I heat up to 6,000 Kelvin to target temperature and then equilibrate for 15 picoseconds with the time step of 1 femtosecond. And so just an idea of the timescale of these simulations, using 10 nodes on Blue Crystal 4, so that's 240 CPUs, takes around 7 days for every 5 picoseconds of simulation. So here I show the experimental and simulation conditions explored. So our experimentally obtained melting curve, shown here in blue, was constrained by observing either liquid diffuse scattering or single crystal diffraction, shown here. So each data point here represents either a liquid or a solid measurement, where every 2 to 3 gigapascals we measured long 20-minute acquisitions in the liquid field. And the crosses here represent the pressure temperature conditions of the simulations. So the power of the ab initio molecular dynamics technique can be assessed by its ability to accurately reproduce experimental measurements. And so here I show the high pressure structure factors for liquid gallium in black, and the ab initio simulations corresponding conditions in blue. And you can see there's very good agreement between the simulations and the experimental measurements and the corresponding pressure evolution. Interestingly, with increasing densification, we see a loss of this first peak in the structure factor, although I note it remains asymmetrical. If we compare this to, for example, to liquid tin from shock measurements, the authors here contribute attribute the loss of this shoulder to a transformation from a complex to a simple liquid. And they suggest their measurements are in good agreement with the hard sphere model. So this is something that we wanted to look at more closely for the gallium measurements. So here's the pair distribution functions, and we can integrate over the first peak here to obtain our average gallium-gallium coordination, where the experimental measurements and simulations show a similar trend, where at ambient pressure, the liquid coordination number is around 10, which is lower than the typical value of between 11 and 12, typical of other liquid metals. With increasing pressure and densification, this coordination number increases, approaching a value of around 12, which would be consistent with simple close-packed structure. But going on this average coordination number alone can be misleading. Yeah, we need a more detailed analysis of the simulation trajectories. And so for this, I approached Francesco Torci here in physics, who has expertise in interpreting structural models of liquids and gases. And he applied his topological cluster classification, in which the local structure of the liquid is described using this predefined library or zoo of many different clusters which represent the minimum energy motifs from various classical simulations. And so in this plot here, if we consider the ab initio molecular dynamics simulations just above the melting curve, this figure tracks how the topological cluster classification features change from low to high pressure and temperature conditions. And so with increasing pressure and temperature, the abundance of these larger motifs increases, and particularly the 10B, this 10B unit, which is a five-fold symmetric, partially icosahedral unit, and this crystalline 11F unit stand out. Although still quite low concentrations, their abundance almost doubles from low to high pressure. And so finally, for every ab initio molecular dynamics data set, Francesco developed a scoring function, here delta, which describes the deviation from the ab initio simulation from a hard sphere structure. And so blue here, the blue color represents the largest deviation from hard sphere structure, and the orange and red, the simulations are closer to hard sphere structure. And so as indicated in the measurements, the structure tends to resembling a hard sphere-like structure at high pressures and temperature towards the melting curve. Although the deviation from the simple model remains very high, above 40% overall pressure temperature space. And interestingly, we find that these five-fold symmetric 10B and crystalline 11F units, as you recall, which increased in their prevalence close to the melting curve at high pressure, are also the units with the lowest configurational entropy, as shown here on these violin plots. And we postulate that the competition between these radically different forms of emergent structural units, but with low configurational entropy, may help to stabilize a metastable metallic glass in the high pressure supercooled liquid. Although this is highly speculative, but could be a route to forming novel metallic glass materials at high pressure. Okay, so I've come to the end of my talk now. I just wanted to briefly say that the other liquids also have very strange melting curve behavior. For example, lithium, sodium, traditionally thought of being a simple liquid, actually exhibits some very deep melting curve minima. And so it'll be interesting to probe how the liquid structure in these deep melting curve minima. And we could apply some of the existing experimental techniques for this, but over the last couple of years, we've also been developing a new technique which we term internal resistive heating. And here, rather than surrounding the dynamos with heaters and heating a sample that way, we actually place the heater within the pressure chamber in the dynamo cell itself. And so then we can, by isolating, splitting the gasket and isolating the two halves of the gasket, we can pass electrical current through this heater. And this offers some advantage over laser heating, for example, because we can obtain wholly molten samples, thereby significantly reducing our signal to noise ratio. And so we successfully use this technique actually at pressures beyond 50 gigapascals and several thousand Kelvin. So it's definitely something which is under development. And Benedict Heinen actually did most of the recent work in getting this technique working. And then finally, the current project which we're working on, funded by Engineering Physical Research Council here in physics, is to develop the technique of acoustic levitation with laser heating in order to fabricate novel glass compositions. And in fact, with using acoustic levitation instead of aerodynamic levitation means that we can use smaller sample sizes and potentially have ultra fast quench rates, and so develop glass compositions which cannot be formed using any other method. And also the small scale of the glass is formed this way. We can form microspheres which would have application for whispering gallery mode micro resonators, which our project partners at UCL are interested in. Okay, so thank you for your attention.